Lab number 2 is part of a sequence of experiments where we're going to make an AM/FM radio. We'll break it into 3 separate experiments of different lengths. This first lab, dealing with the radio, we're going to make the output stage, which is a power amplifier. For us to do that, we need to go back and review some ideas from ECE 302, primarily the bipolar junction transistor. Recall there's 2 types of BJTs, an NPN and a PNP. If you forward bias the base emitter junction and reverse bias the base collector junction, you can put the transistor in the active region. And in the active region there are 2 models, a DC model and an AC model. The DC model is shown here with the base emitter voltage being the turn-on voltage of the PN junction, and the ratio of the collector current to the base current we'll just call beta or beta DC. The PNP transistor, although drawn in some sense upside down from the NPN, has the same effect. Between the emitter and base there's a forward bias diode, and that represents a drop of around 0.6 or 0.7. And the ratio of the collector current to the base current is again beta DC. For the NPN, the base current is entering, and the collector current is entering, and the emitter current is leaving. And just the opposite for the PNP. The emitter current is entering, and the base current and collector current are leaving. If you forward bias a PN junction, you create, as we discussed in 302, a dynamic resistance we called R pi. There's also a capacitance associated with being forward biased. We call that C pi. So in our AC model, between roughly the base and the emitter, we'll have a parallel R and C. This series resistance here represents the resistance of the ohmic contacts between the wire and PN junction. Now between the base and the collector, we have a reverse bias diode, and again a resistor and a capacitor associated with it. The resistor is fairly high in value because it's a reverse bias diode, and the capacitance is that of a reverse bias PN junction, essentially 2 plates separated by an insulator. And again, the same models are for the PNP also. You can find some of this at the bottom of the page here. The relationship between R pi and the biasing point we had derived in 302 is eta F V sub t over I sub b at the Q point. Typically eta's F is equal to 1 and V sub t at room temperature is around 26 millivolts. So the biasing of the transistor, the DC results, affects the AC resistance. So we're able to control some parameters by manipulating biasing. Now in the model on the previous page we had seen there was a resistance in parallel with the current source, and that resistance is coming from the fact that the VI characteristics of the collector current versus the collector emitter voltage have a slope associated with them. The reciprocal of that slope is that output resistance. Now if you take all of these lines and actually extend them into the second quadrant, they actually all come to one point. We call that the early voltage. It was actually discovered, I think, in the 1950s by a researcher named James Early. Noticed that this phenomenon actually existed for all transistors. So if you take the rise over the run, in other words, take at a specific biasing point, really form a equilateral triangle. I can draw this. And so we could take the rise, which would be, if we're solving for resistance, would be the denominator, over the run, which would be the difference of these two, which would be the biasing point minus the voltage here, which is actually a negative number. But this is typically on the order of 100 volts or so. So if we bias our transistors at 5 or 10 volts, you could roughly throw this term away. And most people just approximate the output resistance of the transistor as just the early voltage divided by the collector current at the biasing point. Typically this is on the order of 100 k ohms. The resistor between the base and the collector, when you reverse bias, they call the feedback resistance, and typically is in the range of 5 to 10 megohms. Now for most hand calculations we're just going to ignore this, but SPICE has this built in, so it'll do some more precise calculations than we'll probably be able to do by hand. As you mentioned in 302, there's a term called transconductance, and this is collector current divided by A to F V sub t. And typically something on the order of 40 millimos. Now, also not in the model is shown really an effect of GM and R pi together. The product of GM and R pi is what's called the AC beta of the transistor. We had done in 302 just that. At low frequencies, we modeled the transistor as having a current-controlled current source, but as frequency gets higher and higher, if we include these capacitances, we can have a constant GM versus frequency versus a beta naught, which will be varying with frequency. And so the model is really based on the idea of having a transconductance there of a constant value. The C pi and C mu, as you mentioned, were forward bias capacitance, sometimes called diffusion capacitance, as we had talked about in 302. And C mu is a depletion capacitance. It's a reverse bias type effect. Here's some typical values around 100 picofarads for C pi, and maybe 1 to 3 picofarads for C mu. Okay, it's a real quick review of some of the things we had just touched on in ECE 302 dealing with transistors and biasing. The output stage of the AM/FM radio is using it's called a complementary Darlington pair power amplifier. I thought we'd just kind of work our way through this and kind of analyzing what's there. And did it with a splice simulation. Used a plus and minus 5 volt power supply and a 5 volt sine wave coming in. You can find all these models on the ECE 404 homepage that are listed here for the transistors. On the following page you can see the simulation results, but maybe before we even do that, let's take a look at what's going on here. This stage over here is actually the complementary pair we had built in a couple labs in ECE 303. If you recall, but if you forward bias this transistor as base emitter, which is Q11, you automatically reverse bias the emitter base of Q12. So when the top transistor is on, the bottom transistor is off. And if this transistor is on, then base current can flow through here. Basically, the collector current here is the base current of Q13. So if this is in the active region, we'll get another effective increase in current gain through the additional beta, and we're going to drive a little formula for that in a few pages. And so when the input is positive, we can forward bias this junction and basically create an output voltage that the input voltage minus the drop across the base emitter junction. So very much like the complementary pair we did in the 303 lab. So on page 4 here you can see my input voltage is this 5 volt sine wave. The voltage across the load, which is node voltage 3, has a peak value of 4.24 in this case with models of the transistors that we're using, and a negative excursion to minus 4.23. The input is going to go as high as a peak value. In this case it's 5 volts, although we could symbolically talk about it as V sub S peak. This is our source voltage on the previous page. And let's just scroll back real quickly to see where that formula came from. If you go around the loop this way, this again would be for a positive voltage on the input and large enough to forward bias this. The rise in voltage here, V out, would equal minus the drop across Q11 plus V sub S. And so that's where this came from. So when V sub S is at its peak value, we just have a diode drop difference between this, and then we could subtract those two and figure out the values. So around 0.7 or so. Do the same thing on the negative excursion, and the output voltage, the rise is equal to the emitter base voltage plus V sub S. But when V sub S is at this instant in time, it's really at its negative peak value. So we can roughly predict peak-to-peak value of our output waveform. And because we have this base emitter drop or emitter base drop, we're going to lose a little bit of voltage. And also we're going to need a little bit to turn things on. We'll use feedback to fix up some of these things that we had done in the 303 lab. You can kind of watch what happens as we connect this up with the rest of the circuit. But there'll always be some distortion there because we have to turn that junction on. If you plot the output versus the input, you can see here that roughly have a gain of 1. And what that's saying is that the output, the change in output is the same as the change in input because the drop across the base emitter and the emitter base is fairly constant. So here's the value of voltage of V in before it turns on. The reason these are different is that one's a PNP and one's an NPN transistor on that first stage with Q11 and Q12. And the same thing with slope 1 over here too. You can also see that, if you look at the individual transistors, that when the input is positive, then Q11 and Q13, as we've just shown previously, are on, and that when 12 is off, then there is no chance for base current to go in Q14, so it's also off. And just the opposite happens when we swing negative. Graphed here the current in the collector of transistor 13 and transistor 14. And so you can see here that there's a value and then 0 and then a value and then 0. And then just the opposite here again, just the top half is on when the input's positive and the bottom half is on when the input's negative. If you scroll back to page 3, I won't do it again, but V out, if it's positive, has a voltage across R sub L, and the current in the load, if the bottom two transistors are off, is just going to be the currents from Q11 and Q13, which in this case is the emitter current and the collector current. Now, because the base current of Q13 is collector current of Q11, then this contribution to the summation is pretty small, and you could pretty much neglect this and be roughly the collector current of Q13. Again, if you're in the active region, the collector current and the emitter current are about the same, and this is the current that's actually coming out of the plus 5 volt power supply. What I want to do is calculate efficiency, and so I need to know the value of the current. So let's find actually the average value of this current, and then we'll use that to calculate average power given up by the two power supplies. The average value of current is 1 over the period integral of current over a period. And so what we've got here is roughly a sine wave for half the period, and then basically 0 for the other half, this part over here. So that integral is just 0. We also substitute in that omega is 2 pi f, or 2 pi over t, if you take f as 1 over t. And then we bring this constant out in front, and then the integral of sine is minus cosine, and then the reciprocal of this term, so it'll be t over 2 pi. Let's bring the minus sign out in front here. In fact, let's bring all this stuff out together. And then let's evaluate the cosine from t over 2 to 0. So I'll put t over 2 here and 0. Okay, the t's cancel here. And also so does a 2. And so I get the cosine of pi, which is minus 1. And then the cosine of 0 is plus 1, but there's a minus sign here. So the minus signs cancel. You add up to 2. 2 cancels with the 2 here. And wind up getting the peak value divided by pi. We did a similar derivation in 303 for the complementary pair. So for a half-wave rectified waveform is really what this looks like. Over a period, the average value is just going to be the peak divided by pi. Similar derivation for this one because the shape is the same over a period.